All right, so summary statistics for each exam version given to students are shown in this table below. The teacher would like to evaluate whether this difference is so large that it provides convincing evidence that version B, which is the lower scoring of the two exams, is statistically more difficult than version A. So we start off by constructing two-sided hypotheses. And for this, if we had different groups of students taking the two exams, then this would be unpaired. So my null hypothesis is that there's no difference in the means between the two exams. So the mean from group A minus mean from group B is equal to 0. The alternative is that there is a difference in the means. So mu A from minus mu B is not equal to 0. Does it seem reasonable that the scores are independent within each group? So, yeah, I mean, assuming students are working on their own, it should be reasonable to assume independence. Does it seem reasonable that the distributions of each group is approximately normal? Well, I don't have a graph, but I have the minimum and maximum for each score, so I can compute the minimum and maximum z-scores for version A, and you can do the calculations yourself, but you get negative 2.46 on the minimum side, positive 1.47 on the maximum side. For version B, 32 minus 74.1 over 20, that's negative 2.11 on the minimum side, positive 1.30 on the maximum side. All these scores are between negative 2 and negative 3 and positive 3. So there are no apparent outliers, and the sample sizes are both above 30. The assumption seems reasonable. And do you think the scores in the two groups should be independent of each other? So that is, the two samples are independent. That is, that the results from one group has nothing to do with the results from the other group, or knowing that someone is in one group has nothing to do with whether someone else is in another group. And yeah, if the exams are randomly assigned, then the results from one version exam should have nothing to do with the results from the other version. Alright, so for the standard error, again, take the square root of the first standard deviation, so that's 14 squared, divided by the first sample size of 30, plus the second standard deviation is 20 squared, divided by the second sample size of 27. And I get a standard deviation of 4.62. The test statistic, well, the point estimates are 79.4. Well, test statistic is point estimate minus null value of standard error. The point estimates are 79.4 and 74.1, so the difference is 5.3. 5.3 minus 0 over 4.62. Well, if I just go 5.3 divided by 4.62, I get 1.15 for a test statistic. So from there, compute the p-value, or well, actually, the degrees of freedom. Smaller sample size is 27, so the degrees of freedom we'll use is 26. Go second, bars, TCDF. My test statistic is 1.15999, 26 degrees of freedom, paste, times 2. And my p-value is about 26%, so that's well above 0.05. That would mean fail to reject the null hypothesis. We have no evidence that the two exam scores are statistically different from each other. So, again, sample sizes are 30 and 27, so there are 26 degrees of freedom. The p-value is a TCDF. It's the test statistic to 999 degrees of freedom times 2. I get about 0.261. The p-value is more than 0.05, so we should fail to reject the null hypothesis. There is no evidence that the two versions have different means. So, any differences in the sample is just likely to be random chance. And one note, The actual degrees of freedom are approximately 45.9726, and the p-value is 0.25728. So both the one I computed with the other degrees of freedom and the actual p-value, actual degrees of freedom, comes out to be p-values of 0.26. So how does our calculation of the p-value in the previous example compare? Well, our calculation is slightly higher, 0.26 versus 0.26, but both round to 0.26 again and give the same conclusion. There is no evidence that the means are different. So you can see that even though I went with the easier to compute degrees of freedom, it really has very little impact on the p-value.